Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to use some rotations in order to solve a geometry problem. But first, let's start with some review. So first of all, what is a rotation with the center O, and the angle of rotation is given by the angle AOB? And when we write it like that, we're thinking of the rotation that moves A to B, right? So there's a little bit of directional information in there other than just the angle itself. So let me give you a moment to think about it, see if you remember how we defined it from last week, and then we're going to go ahead and review the definition. Okay, so the definition we did last week uses the composition of two reflections. So let's break this down. The first thing we do is we construct the angle bisector of the angle AOB. And then, of course, we have a distinguished line, which is the line OB itself. And our construction is, the first thing we do is we reflect about the perpendicular bisector. So here I send the point P, then to the point Q, right? I reflected that across, I said perpendicular bisector, I mean the angle bisector. We reflect across the angle bisector here. And then we reflect Q across the line OB, and that gives us the point P prime. So that's our definition of the rotation with center O and the angle given by AOB, where we send A to B. The reason we did this was we found it difficult to make sense out of rotating in one direction versus the other otherwise. And this is a very convenient way of representing the rotation for us. Okay, next thing to review, what is the translation from A to B? Let me give you a moment to think about that, and remember we defined it involving a composition of two reflections. So here what we did was we constructed the perpendicular bisector of the segment AB. We constructed a line perpendicular to AB incident to B. And the first thing we do is we take, so here my input point is U. I reflect it across that perpendicular bisector and I get this point V. And then I reflect V across that line there, and it gives me U prime, which is now the translated version of U. So U prime is what we get by translating U using the translation from A to B. Okay, so that's our nice little review here. Let's set up the problem. So the problem for this video is we're given three concentric circles, and I've named them CA, CB, and CC. Now I'm going to remind us, in case this piece of vocabulary is unfamiliar to you, concentric means that they have the same center. So I have these three circles that have the same center, and I want to construct an equilateral triangle with one vertex of the triangle on each of my circles. Okay, this is maybe a strange question, a difficult question. Let's break it down a little bit in some steps. So first of all, can we always do it? So if you think for a little bit, let me let you think about that for a moment. Is it always possible to do this? Well, the answer is no. If my radii are too dramatically different from each other, it's not going to be possible. So here I have an example. My two inner circles have relatively small radius, and my outer circle has a huge radius. And the reason this is impossible is, let's say I have a point here, I don't know, let me call it B. right? And then A is supposed to live somewhere on my inner circle. So there's my inner circle. And the farthest from B it can get is that distance. Right? That's the farthest it can be from B. But if I want an equilateral triangle, right, so that distance there is whatever it is, that's the maximal distance between B and A. But now the smallest distance B can have from C is that distance there. Right? And that purple distance is bigger than that pink distance. So it's going to be impossible for me to even make an isosceles triangle, isosceles in B. So there's no hope of constructing an equilateral triangle. Right? So here the problem is we can't even make an isosceles triangle. Okay. Are there easy cases to solve? Well, here's a sort of a silly way of solving the problem, which is cheating. What I'm going to do is I construct an equilateral triangle, and then I put the circles so that it works. Okay, so here, for instance, I constructed this equilateral triangle ABC. And I chose some point O that's not on the triangle, and then I drew the circles. So in this example, I chose my point O over here, and then I drew the circle centered at O that went through A, the circle centered at O that went through B, and the circle centered at O that went through C. So this is a configuration that solves my problem. Right? If you'd given me these 3 concentric circles, then I could put ABC on top of it after the fact. And so that's kind of cheating. But this is a useful solution strategy in general, where you start with something where you have an answer, you pretend you have an answer, and you work with it to figure out what properties it has to have. So in general, the idea, right, if you want to construct a solution to a problem, you pretend you have a solution, you monkey around with the solution to see what has to be true, and then hopefully this nails down the solution. And so from a conceptual point of view, this is an incredibly similar strategy to what we did last week in defining a rotation as a composition of reflections. Right? To figure out what the reflections were, we assumed we knew how to make the rotation and then played around with that. Also, if you think to how you solve an algebra problem, that's secretly how you solve an algebra problem. So for instance, if I ask you to solve the equation x equals square root of the quantity 1 plus x, you pretend you have a solution, you square both sides, you get a quadratic, you solve it, and then you check which of the 2 solutions to that quadratic you had actually solved my initial equation. Right? So that's a classic way of solving algebra problems, as well as solving geometry problems. Right? So this is a widespread idea in all of mathematics. And now, here's where the symmetries come into the story. I have my 3 circles, and I have my equilateral triangle. Well, a really nice thing about an equilateral triangle is it is symmetric under a rotation by 60 degrees. And in particular, if the center of the rotation is one of my vertices, so for instance, if I take here the rotation centered at B, and I rotate by 60 degrees in that counterclockwise direction, A gets mapped to C. So we're going to leverage that and say, okay, imagine I have this triangle ABC, and it's an equilateral triangle. B is on the middle circle, A is on the inner circle, and C is on the outer circle. Well, if I rotate A by 60 degrees, I get C. But what I can do also is I can take the whole inner circle and rotate it by 60 degrees, and that's how I end up with this red circle I have here in my diagram. The center O maps to a new point, O prime, and this point O prime is the center of that red circle. And the key feature then is that C is the point of intersection of my red circle with my outer circle. And that constructs for us a way of describing C as an intersection of two circles. I take the inner circle and I rotate it to get my red circle here, and I intersect it with that outer circle. So the algorithm for the solution, what we're going to do is we're going to choose an arbitrary point on the middle circle and call it B. Now this makes sense because if I'm able to solve the problem after a global rotation by whatever, I can move B to be at any point on the middle circle that I like. Okay, so I get the freedom to choose the point B arbitrarily. So I do that. And then now I play that game. I rotate the inner circle by 60 degrees centered at B. And now I either have 0, 1, or 2 intersections of that rotated circle with the outer circle. And in the picture we just looked at, we had 2 intersection points, but circles don't always have to intersect, and they can also be tangent to each other. If there are no intersection points, it's impossible for my equilateral triangle to exist. If they do intersect, we get either 1 or 2 choices for C. And then now once we have B and C, we can construct A using Euclid's construction of the equilateral triangle. Remember, that was proposition 1 that we saw ages ago at the beginning of the semester. So this is a little bit hard to follow here in this wall of text. So let's cut now and take a look at what this looks like in GeoGebra. Right here, I've started with my 3 concentric circles. They all have the same center at this point O that you see here in the center. And I've placed a point B on my middle circle. So now what I'm going to do is I'm going to take my transformation tool, and I'm going to rotate, and let's do 60 degrees, and here I can choose either clockwise or counterclockwise. I'm going to choose clockwise, just for fun. And this makes me a new circle here that I get, which is the rotation of my inner circle. And now I'm going to choose one of the intersection points of the rotated circle with my outer big circle. So I'm going to choose that point there. And so now I have a point here. I'm going to call it A. In the notes I was calling it C, but it doesn't matter. We're just going to have A be the guy on the outside one. And now I'm going to construct the equilateral triangle. So I'm using the regular polygon tool. And this is going to construct for me the equilateral triangle where it's going to have the vertices going around counterclockwise. So I'm going to go B, A, and then I'm going to tell us I want 3 vertices. And boom, that makes me the equilateral triangle I wanted, with a vertex on the middle circle, a vertex on the outer circle, and a vertex on the inner circle. Now you might ask, what happens if I choose a different intersection point? And we can totally do that, right? The other intersection point I had from that circle is this point here that I've now labeled D. And we can repeat the same general construction. I take the regular polygon tool and right? B, C, okay, and I want 3 vertices, and that gives me, boom, another solution to this problem. So something I'll have you think about a little bit is what happens if instead of doing the clockwise rotation, I'd done the counterclockwise rotation. So that's maybe a little bit fun to think about, and that illustrates what we just did in the notes. Okay, now that you've seen that in GeoGebra, I'm going to give you a slightly easier variant of this problem on the homework. So the question on the homework is we have 3 parallel lines. And the question is to construct an equilateral triangle so that you have a vertex on each of the 3 lines. So I ask you to come up with a construction method of that. And again, you're going to find it very useful to think about this rotational property that equilateral triangles have. Okay, that's it for this video. Thank you for watching. Good working on that homework problem, and I'll see you on the next one. Happy mathing.